All right, and then let's talk. Yeah, what is the question here? Okay, it's not that. Is that like is that the student like watch my video, or it's quite disappointing to see like only like a couple person attend the class. I hope that they can watch the video too. Is that 10?
Yes.
Yeah. Okay. Hopefully they can. Yeah. All right. Okay. Let's start. Okay. Again, I just repeat. The agenda today will be like there's a two half. The first half, which is the first hour, I think I will finish the class with the last chapter, the physical design. This portion will be physical design, the steps of physical design, and the second part will be your question, answer your question about like whatever question you can have, so that like we can make a good exam, good test for the final test. Hopefully this time I think we learn the lesson, and then I think we got a better result. And if you don't have many questions, then I think I might like talk a little bit about whatever the question about like you can have any question about what's supposed to be here, or like what you want to know about the job market or the study here and so on, whatever. All right, let's start with the. So first, I follow the slides like the framework from Dr. Phạm Từ Hai, and then I think this one. However, this one is quite short, so I will have some extra slides to explain like the steps we will have to do in the physical design. The PNR, which means placement and route. That's because it starts with that, because in the old days, it's really only placement and route. But as the technology advanced, it get like complicated. Then there will be like a different step in there. Like we have floor plan at the beginning, and then we have the CTS, and the route is not only route, but there's also route and post route. And in the route, there's a global route and detail route. Place, we have a pre-place and placement. So on the left, you will see that on the left is the top placement. And then let me see if like you see do you, okay, yeah. So let me see, I think maybe I can show is that section. Okay, or no, it's not. Okay, all right. Okay, actually on the left is basically is this one is a little bit, I think a little bit like it's not very correct. On the left is quite like the floor plan at the top level, not the top placement, because placement usually is talk about the placement of the standard cell, not the macro. So here I think it's like this one is a top floor plan, and floor plan. We'll talk about that. So floor plan, talking about floor plan, it would be like basically it's about the placement, or like the location of the macro or of the subblock. At the top level, you can see that here at the top level, right? This one's the whole chip, and inside will be subblock. So the floor plan means that we have to like negotiate the real estate, or the area and the shape of each block together. So the way that so that means the floor plan means like the floor plan of the house, floor plan of like of area. So we just like put that like the shape basically the shape and the size of each block. And inside each block, we will like place the where we place the macro, right? On the left is the top level, which is each block here. So if you can consider like each block is like a big macro, right? Big macro. Then you have like this one, we have a big macro. Inside this big macro, we will have like a small macro, like uh, uh, hierarchical macro. So here you have that, and then you see that those in this part that doesn't have any macro or block here, it will be standard cell. What is standard cell? I think we explained that before, right? Standard cell is the logic cell, the basic logic cell is like a buffer, inverter, and or NAND or AOI, OAI, multiplexer, flop for sure. So those kind of things is like those things, they are standard cell. Along with maybe beside the mux, maybe we can have also like a adder, half adder, or maybe we have the macro like the multiplier or like something like that. So with like so that means like you can see, yeah, all the definition here is basically is for the floor planning. We have the IO, analog macro, and then the RAM, ROM are placed. These things we place where, like, that means we place at the location and we negotiate and we agree on that on the top level. I use the term negotiation because each block here will be owned by a team. So because by a team, it's a different team, so that means the top guy, which means the guy who does this top level, will have to negotiate with each block owner to like arrange the shape and also arrange the location of the port. Let's say you have this one is a block, right? And this one's on so another block. Here you don't have anything like it is kind of like a abutment, which is like this one. They are placed next to each other. It's called abutment. It's abutment. So abutment means you put two blocks next to each other, and the signal like go from one to the other by the abutment, which is like this. There's one here, and the other one is like this. The signal go here, and then just go like that. So the port will be like this. Then by abutment, it just connect like automatically. We don't need any routing. That's called like routing by abutment. But the problem with that is it's not like easy to do that every time, because let's say like this block. Let's say if this block need to not only it talk right, not only it talk to this next block, but it can talk to this block. So in that case, you cannot put like everything. You cannot put this one on top to be abutted. Then we need to have like something go out here, right? So I just make like a sample. In this case, it looks like this block. It looks like it doesn't talk to this block, because you see that it's not like it plays far away, and it's also like you have this thing is like the one where we have the space. It's not much. So this block, if it want to talk with this block, it will have to go this way. So this one and this one is seems to me like they are like a heavy communication between the two, which is like it talks. When I say it talks, I mean like there's a signal back and forth between the two. So with that, they place to next to each other, but they still cannot abut them together. The reason is like to be abutted, it need to be like in order, right? And it's not easy to put it order. Yeah. You said, let's say like one here in order and also in a very strict like space. So it's not easy to do that. So you see that we have it here, but it's not like it needs a very like a close coordination to have that abutment. Okay, that's so on the left, all kind of things like block shape are decided, power and ground grid is designed. These tasks are done in the floor plan. Position to place pins for each block is a place. Again, I don't know why they put the placement here. This one's supposed to be FP. And then we have that is, and now when we go into like each block, you see that those things here, that's the macro. That's like a macro. It can be like with the things like it's supposed to be like a small memory. This one's a big memory, or like something like it's something like a big macro something. So you can see that like all macro usually they will be put like around. There's a reason for that. So I will like explain later. So the same RAM ROM analog macros are placed. The multiple port are placed. So that means they have to define, right? They define the ways to port. These port need to be negotiated during this one. And then power ground grid is implemented at the block level. At this top level, they will have a power along that. And you remember when they do some simulation, they know like, oh, this block will consume a lot of power. Then they will have to put at the top level. They will have to like consider to put the lot of metal here. That means the power grid here will be dense to provide enough power for this one. If this one consume a lot of power, the other one they don't need to do that if it's not consume a lot of power. The same thing but now this one is the top, right? Which means like it will use the top layer. Let's say the top layer here is we have a 15 level, right? M1 to M15. So the top layer here for the top level we will be using two layers, middle 14 and 15. If is 15 layer, if 14 it will be 13, 14, and so on. So when they do that, they do a top level, they provide that way. Now when we go to this block level, so there's two ways to do the block level with the power grid. Either they will use the power grid like from like they will use the power grid will be like the same as the top level here, which is let's say like because it built like from bottom up, right? When it's a bottom up, which means like this block owner or like this team doing this block will implement the power and the ground grid here, implemented that, then it implement up to like level 15. Then when it just let's say this block is this block, right? Let's say it's this block. And when it put in here, it just go like the whole thing here is go up all the way to middle 15. So that means that the top level won't have to do anything for the power grid in this case. So in this case, this portion would be like the power grid will be done from this guy, and then the top level will like inherit that. He will not do anything like power grid for this block. There's another case when we have like when we have the power grid will be done like at the top level. So this one will have to, let's say this one is do the power grid for 14 and 15. This one won't do it, then it will limit the top level of that up to middle 13 only. So it won't have the power grid inside here if the power grid is done at the top level. So that's for you to have some idea. Now, placement optimization. This one is really like the placement. So for the placement, okay, placement. This one is really like a placement because placement include like a pre-place and optimization and post optimization. So this one doesn't need to be mentioned as optimization. It's just a placement. So that's why you see that prerequisite is a design after floor planning, right? That means like after we place everything like that, we will like start the placement. Placement basically is like the step that it will place every standard cell. Yeah, logic standard cells are automatically placed by the EDA tool by the placement step. Okay, During this step, during the placement, okay, I will explain like why this step happen. So because remember, the purpose of our design is like PPAS, right? Performance, power, area, and dollars. So the first goal, first and foremost, is about the performance, which is about timing. So in the timing, so to be able to optimize the timing, the placements of the cells need to be optimized, take, taking into account the timing too. And then taking into the account the timing means the while delay and also the cell delay, right? The cell delay is all one. That the while delays affect the cell delay. Remember, when you have the while is long, the cell delay will be higher too. And when you have the y length is long or like is narrow, the y width is narrow, that means there's a the basic thing to have to consider with the y delay. First, the length. Second, the width, right? The length is longer, the width is narrower, then we have more resistance and more capacitance. So which is, I think there will be like we try when we place the cell, we try that in the tool, we'll try to place that for the like closer, but you cannot like put everything in the same spot, right? Because you have this, it has everything like this. You cannot put to be like put everything close. You cannot put it in one spot like that or one small area. It will be hard. It will have to spread all over here because the signal or the data part, the timing part will go from this macro to this macro, from the memory here to memory here. So it will be like the cells will be spread all over the place. You see this? This is the space that the tool is allowed to place the center cell. How do they play that? They have a criteria. First of all, they need to have like okay, now is the target is the frequency. Then they have a, but how do they know that like the timing? So they need to have a, remember we need to have some like referee to know that, oh wait, this pass along. So we need to have some like anchor to compare that with the timing of the part, which is the clock, right? So because in the placement we don't have the clock yet, because we don't have a clock yet, so we have to assume that, right? For example, let's see like this, right? Go and we have that here, go to the another one, and then clock go like this, come from the same, right? So D here, and Q. Let's say that it's like we have a data part. I think the data is here. Now this one is the clock. So the clock going to like the first one and the second one, right? It won't be the same because you see that like because these two flops are at different places. Then when you have a clock, you go like, I think last time I already like explained, the clock won't be like won't have the same delay, which is you have the delta here, and it's called like clock skew. Fine. But during the placement, we don't have any clock. We didn't do any routing yet. We just placed the cell. So that means there is no clock. So in that case, we have to proceed with like whatever we have. Then we have to assume that like the clock is ideal, which is now you have the arrival time at every flop. Every flop clock input will be 0. So in the placement, they just consider everything that like every clock come to like the arrival time of the clock to every flop will be 0, which is like perfectly ideally synchronized. All right, so that's not a choice, but we have to assume that so that it's better than nothing. We need to have something like to refer to, so we have to do that step. When we proceed, we have more information, then we will like we'll update our data, right? The second thing is that the connection are virtually routed. What does this mean? It means let me did that, then I'll explain again. Now let's say like here I have this one go to like this and go to this and go to like whatever and go to the next one, right? So we have this thing, this thing, this thing. So this flop and this flop is this one is a launching, right? This one is a launching flop and this one is a capture. So you see that like here this cell will be placed, this cell will be placed, and this cell are placed during the placement. So when they are placed, how can they know like the y here, like what is the y here, right? So if in the, let's say in the, here's the chip, I make it like I amplify that. So this one here, this one here, this one here, and this one here. Let's say like it's one and cell one, cell two, and flop, right? It's a F1 and here's a F2. So let's say like this one's a F1 and then C1, C2, and F2. During placement, we can only have those cells placed like that. There's no route. So the tool need to run some like a virtual connection. That means that they assume like you have here there is a Manhattan distance. Manhattan distance is just like they do like a simple like that, which is a perpendicular distance. If you have a two cell like this, the Manhattan distance will be like a perpendicular, just at that, because in the chip, right, it can only routed, it can only be routed horizontally and vertically. There's no other way. There's no like ortho the way that like orthodontically or sorry, I forgot the name. There's no way to like route like this in general. That's allowed in like that is allowed in the old days, but now with the complexity of the chip, it's not allowed that way. Okay, then because it's round like this, so that means that basically the distance between the two cells is a Manhattan, right? So they have that. So they will assume that like the route go from like flop one, go from flop one here to like the C1 here will be this Manhattan. Okay, Manhattan is like Manhattan in New York. Manhattan distance, right? It will write that. So by assume that way, they have some, at least they have some like estimation quite better than like a wide load model, right? So we have that. So if you have a distance, so then I assume that like those route will be or like will have the minimum the default route. Actually we have a default route, the default route rule, which is a minimum width, minimum space. Usually with that they have the minimum information like that. They can calculate, okay, now when it's placed like that, right, the flop one is here, C1 is here, C2 is here, and the flop 2 is here. Then they can calculate with that, assuming with that like assume Manhattan distance. They can calculate the y here, the y length, and y capacitance and resistance. So with that they have all the info, so that like the rough info is not correct, but it's like approximate. So they can calculate delay from here until here. When they can calculate that, then they know that, oh, these parts are how many, like what is the timing through this part. Then they can compare, they can see like if it meet the target or not. If it meet, it's okay. If not, they have to move around this one. Oh, now it's too far away, right? Now I have to move this one up here. And along the way, these two will move up. So that's like in the placement, there will be two steps. One, the pre-placement with the rough calculation. So they put like quite they have like a kind of like some seed. So they just put a seed. That means they just randomly at the beginning like and then from there they will calculate and then they readjust. Yeah, so there's the logic can be optimized and sender cell can be changed or move to the other places to resolve the routing congestion, reduce timing, and perform power optimization. This perform power optimization here. This one is be the last thing to do during the placement. So the thing is like we have so there's a two main thing. It's a timing violation and routing congestion, right? So the thing is there are a couple of things. Not only that, first of all, they will have the cell like they map right during like the netlist. They map like have something already. Let's say this one is one like the strength of the driver is a 1x, right? That means like the strength is ranked as 1, 2, 3, 4, 5, whatever up. Then we have yeah. Then let's say like initially it will be like a 1x. Then we see that oh this flop drive a quite a long route. We need to increase the driver like upsize the driver so that it can drive like a longer route. So it may become like a 2, but it's still too long, so it's a 3, and so on. So that means that they have to like they have that means the loss can be optimized. Optimized and standard cell can be changed. These two things like it means. These things mean like we have to like first of all, I think we it can do some like minimal logic optimization, which is that they can like group, right? Like the last time I talked, you have the AND with the OR, they can group that into the AND OR, right? One cell. Or they can like do the logic minimization, which is like do some kind of like logic manipulation to make it better. But that one is like that function when it works in the placement is a very minor. The main thing they do here is two things: the placement and also like the logic can be optimized and standard cell can be changed or changed. This thing basically is about the size and the VT. There's a two things that it need to be done uh, during the placement. So when it plays initially, it plays like that, and then when it look it back, okay, this is C1 is too weak, will like increase the size. This is C2 is too strong, we reduce the size, and so on. The design rule check and timing check are performed and violations are resolved automatically. This one by replacing or moving cells. That's what I'm talking about. But the design rule check here actually is a very minor here at this step. They will like because here we don't have design rule check. Basically, it's about the design rule for the routing, right? So design rule for the routing is like the minimum width, minimum spacing, the minimum via, or like the end route rule, or like the route of like middle 1, middle 2, middle 3, and so on. There's a lot of like the rule is so complicated that like we have like to check the DRC, it takes hours, even more. I think check maybe like it take maybe like in the half day or something. So this one really, I think during the placement, the design rule check or like try to fix the DRC. There's a no route, so that means that there's a no fix here. All the timing check, right? Only the timing check is done so that like if it doesn't fix, it will like replace or moving cells. That's the doing. Replacing means upsize, downside, change the VT, moving cell. That's why I mean it's like a closer or like if in case like oh this one, let's say this one and this one is a very only like a 10 micron away, 10 micron, and it doesn't need to be like that, and it can be moved away so that it let's say like this portion is more critical than this portion, right? Then if we can move this portion closer to the C2 so that like C2 C1 to C2 will be better, and this F1 to C1 can be longer. So that's a moving cell. So those things is the job of the placement. Now is that I think here I think I go through and I go back to the other one so that you can see that the next step will be like the clock design, which is this one is CTS. CTS. The CTS is in the old days. The CTS, the first. Let me see if it has. Okay. Okay. In the old days, the CTS, the goal of CTS is to build a clock tree which is balanced to all the flop, which means like the arrival time at each flop will be equal. That's the goal. Will be equal so that it become like a ideal clock, right? You know, you remember the clock skill because the clock skill that the timing in one part maybe like the requirement is 1 nanosecond because the clock skill is reduced to 800 picosecond, so it will be more difficult to meet the timing, right? So because of it, like we try like at the beginning we try to make it everything like arrive at the flop, every like the clock arriving at the flop, every flop will be the same. However, that's like ideal, but in practice it's not really good. Why? Because everything was not born like equally, right? We are not born equally like either. So the same thing here, which is there's a part very short and a part very long. This part only like 3 or 4 like level of logic. There's a part like a 20, 30 level of logic. So for the part with 3 or 4 level of logic, that part is maybe let's say I make up a frequency as a 1 gigahertz, which is you have the periods of 1 nanosecond, and then you have the part of only 4 stages. So that part, let's say like each stage has a 20 picosecond. So you have a 4 part, it's only 80 picosecond. So for 80 picosecond, which means like that you don't like it largely meet the timing requirement of 1 nanosecond, right? Because the max delay of that part can be like up to 1 nanosecond, is still the clock still function at 1 gigahertz. Now the other part, it may be like a 30 stages, 30 by let's say that, but it's like a 40 picosecond each. So 40 by 30 is a 1.2 nanosecond. So that one, it will exceed the the period. So that means like those parts are not like will not be optimized equally, which means the short part of 4 stage won't need to be optimized because by itself it meet already. It meet the timing requirement. The other parts with like for 30 stages is of 1.2 nanosecond. We need to optimize it to meet the requirement of only 1 nanosecond. So how can we do it? Then we just like borrow time from one to the other, right? So we borrow like let's say like this. Here is the just like this part is the first part. This one is only 4 stage, right? 4 stage. You go to the next one here. So this one is like a 40 stage. You hold this a flop here, and flop here. So this one 4 stage. This one is 40 stage, right? So this one, so this one is very difficult to meet the requirement, but this one is easy. So the thing is now because of 4 stage, so I don't need this one to be like fast. So that means even like the period from here to here is 1 nanosecond. But now I will make the clock. The clock come in here, right? Come in here, and the clock come in here, and the clock come in here. I make the clock come in here like arrive earlier. For example, here, this one, this is a clock come into the. This one is a clock 1, sequence 1. This one is 2 and 3. So the this one is seeking 1. Then I have like a if it's ideal like that. This one ideal, right? Ideal, which means like we have the perfect like a perfect arrive time at the same time. So in that case, you have like the period like from here to here is 1 nanosecond. But this one's only like 4 stage, so I don't need that long. I make this one then I make this one like short, like arrive earlier. What does that mean? Ah, I will make that this way. So I will make this early like this. No, in this way you think that is, yeah, I would make it early like this, even early, like much earlier. So the right is first sash is first sash here and the edge here, right? So because so that means you remember that when we check the time, the setup, it go from like the first edge to the second edge, right? So from here to here, I think it's like you know, the whole thing is a 1 nanosecond, right? The whole thing here is 1 nanosecond, which is from here to here is maybe like 200 picosecond, right? From here to here is a 200 picosecond, which is like largely enough because the fourth stage it stays let's say like 40. I just make the same thing, 40 picosecond. Then fourth stage is a 160. If this one is a 200 picosecond, then it still meet the requirement of the timing, right? But now you can see that now the next one from flop 2 to flop 3. So now is when it's already flop 2 here, right? It's flop 2. It will like it's launching from here, and then it will be like let's say like you have the what? Okay, because the clock 3 will be the same. I just like clock 1, 2, 3 the same, but clock 2 I just make it earlier, right? Earlier, so that like I save that for the 3. So the now you look at the clock 3. Clock 3 will be the same as clock 1 here. Clock 3, the same timing, the same arrival time. So you see that like this one is the first edge, this one is second edge. So the second edge is here, and the third edge will be here. So that means like the clock 3 will be like capture at the third edge. So you see that from here to here, it's no longer 1 nanosecond. It will be like 1 nanosecond plus this one, right? So it become like if you have here is 200, right? This portion is 200, so this portion will be 800, and then like this period will be 1 nanosecond. So the total time for that will be 1.8 nanosecond, which is here you have 40 stage. It stays 40 like a 40 picosecond, so it will become like a 1600 here, right? 1600 here, but you still have here is a 1.8, then you meet the timing too. So that's why like it's not always the clock would be like it's not always the clock would be like a balance is a good thing, but in general this thing is only for the critical part, right? For the critical part, usually we are happy with like if we have the clock is a balance, that's the best thing happen first, and later on when we do the things that we skew the clock to have a different like this, that will be later step, and that later step actually now become like included in this one, because during the clock they will route it, they will route the thing, and they know now they route the clock, right? They do the clock and then they route the clock, so the clock will be routed first, and then it will be calculated. So after the CTS we will have the real clock, so the real clock, so everything is precise, accurate, and then we can like take it and we estimate the timing, it will be accurate. It's not like in the placement it's all estimate or like a kind of rough estimate based on the ideal clock. After the CTS they build the clock, right? They build clock. I think maybe not here. So remember, I think I show you like the clock will have to go to every input of the flop to provide the clock to be sync up with every other flop. So that's like so that means that this one is like there's two steps. One step is a balance the clock. The second step it will be like they call that like a useful skill. You remember when we have clock skew, if it's not in our purpose, if you don't want that, we don't want that, we just call that clock skew because it's harmful, right? It's a hurt. Because let's say that instead of this clock is like skew, but instead of skew earlier here, it's skew later. When it's skew later, it will eat into the period of the next stage. That's hurt, right? So we don't want that. So we want that skew into like this way. If we want that to this way, that's we call useful skill because that skill is a useful. So that's why it's called useful skill. So the second step of the clock of the CTS will be like a useful skill so that to meet the timing. Now I think after you route the clock, you have the clock here, how much already. Now you know that you want 4 stages, this one's 40 stages. Then we can like just skew the clock to meet the timing roughly again. Still there's a no, we only have the clock routing, but we still don't have the routing for the signal, right? This one is for the data, and here's the clock. So until now we proceed. So we do proceed until the step that we have the clock routing, so the reference is more precise. So after that we will timing driven design. I don't know what to talk about. So this one is applied. So the timing driven design, it means that like when you do the placement, when you do the clock tree, when you do route, everything you keep in mind for the timing. So every time, let's say like we do the clock, we have this, right? We just we build the clock tree. Then we always have like keep in mind like calculate the timing of the data path to make sure that it meets the timing requirement. So the first and foremost purpose of every step in the physical design is timing, and everything else will be like secondary. So I think in the timing, timing is a path delay value, or maybe I think is the most is the key requirement is the frequency. Let's say if we want the circuit, the design work at 1 gigahertz. From there, it will come like the constraint for the delay, for the setup, and for the whole time. So in that, I think it will be too into detail. So you remember like in the SDA chapter, how to check setup, right? The setup time requirement is not the period. That's the period minus the setup time of the capture flop and minus the whole time of the launching flop. And also like is in that you still have you also have the clock to queue. So those kind of things you read the SDA to see like what is the setup time, what is the constraint of whole time. And yeah, okay, here so you have that like this one is an example. Let's say like for setup violation happen, it means like setup violation happen, it means that you don't meet the delay. So which is like the delay need to be reduced. So in this picture, it assumes that like this y is long. So it insert the buffer so that like when the y is long, the best way to like reduce delay is to insert the buffer. Insert the buffer will divide the y length into half or a third, right, or 3 times, right, so that like when it has that, and then it will optimize the total delay. I think that like go back to like my previous lecture, you will see why. And then there's another one is like they can like increase the size, right? You increase the size so that it can drive further. So there's a couple ways. You increase the size so that it can drive further, like a longer while. If like you increase, but it's not like increasing the size of the cell is not the best solution, because you increase, there's a certain sweet spot. You increase too much, then you have the input cap here is increased, and then you have like even you better at the output, but you'll be worse at the input. So they always like a sweet spot for the size of the cell. So you increase the that, and likewise for this one, for this all cell here. And after you increase a certain level too much, then you don't see the improvement anymore. Then you have to insert a buffer here. For example, this one is just like this step will be done. This one will be done in a placement. It will do that. Now it's for the whole violation. If a whole violation happen, it means that like it means that you have this like delay is too long, so that like so that the second flop here will be captured during the first clock edge. Remember, the whole check will be like this. Let's say the second one here is the clock second one, right? So this one is like the check. So that means this one is the launching, which is this one F1. This one is F2. So this one's F1. This one's F2. So when it launched at this edge, and then we have checked this one is the first edge of F2 too, right? So we will check like from here to here. So the delay of this one need to be like more than this. It need to be like here. Why? Because if it available in this like area, then it violates the whole check, which is you want to make it like a longer. For whole, you want to make the path longer. For setup, you need to make the path faster. This one you want to make it longer. How to make it longer? You remember, you reduce the size, right? You reduce the size, and then like you insert the buffer. Again, this buffer insertion here is different from the buffer insertion here. Why? In this case, this buffer insertion like from here to here is not long while at all. In this case, when we insert a buffer here, is we need to insert because it's a long while, then we need to insert buffer. So this one is needed when the long while. So I think for example like this one is long while, and this one is a short while. So because it's a short while, right? So you don't need to insert a buffer. If you insert, it will increase the delay. But for the whole time, you need to increase the delay so that like the data available later, right, will be available here. You don't want the data like to be available early, because early in this, it will be like captured by this edge, which is like a violation of the whole check. So remember, okay, remember for setup, need like a faster delay, and for whole check, it need to be longer, right? So there's these two like go opposite. So that's why there's like always we have you cannot put this one longer forever, right? If it's too long, then I think it violates setup. And this one you cannot put it too fast, because too fast, and then this one will be like violate the whole. There's like one good thing, not good thing, but a lucky thing, that usually these two parts are not the same. The violation of the setup and the violation of the whole are not the same, because let's say like let me, I think I have to find a space to I don't want to go to the whiteboard. So let me okay. Okay, let me draw somewhere here. Here is okay, let me clean it up here. Okay, now between this, right, this one is a flop, let's say flop 1, this one is flop 2, and this one is flop 3. This part go here, right, and then you have this one go like you have this one here and go this way. So you see this part 1 here, P1 here, and it's P2. So you will have like we will have the part 1 here is very long. So this one will need to speed up. You need to be like sped up, but this part here will be short. So this was short, so it risks that it will make the setup easily, but it need to be watch out for the speed. So it need to be slowed down. So the P2 need to be slowed down and P1 needs to be sped up. So these two parts are different part, right? But it will have a common part at the end. See that at the end here, it will have to common some part so that it go into the same D here, D input here, right? So this one, let's say like put it simple here. Let's say that it's the this one is the you go to the end, for example. See, this one go to the end that, and this one go to like maybe like a 20 stage here. So you have the P1. The P1 will go to like 20 stage here to go to here. So it will be like set up sensitive. And this one is already 2. So you can see that usually the whole check happen different part than the setup. So but you will have the constraint at the end always. Layout extraction. I think we maybe run out of time because the second part will be okay. I think it's so layout extraction. This one is a simple. You have this one. You see that this one is the width, the middle y, right? Those middle y here. So these two is a perpendicular. So you have here. Let's say middle 2 here. Then middle 3 will be like that, and middle 4 will be this, and middle 5. Sorry, middle. So I just put like different color so that you can see. Yeah. Now here's the middle 4. So the even layer will be horizontal and the odd layer will be vertical. And now middle 4 is like this, and so on. So when they have that, you see that here on the left, you have the field capacity. So which is this one is the capacity between the Y versus the substrate. And the substrate here doesn't mean, I think, okay. So it's substrate, but I substrate here usually because you have a, let's say, a middle 5, 6, 7, 8, or whatever is very far from the substrate. So that one, so usually we have the capacitance is extracted from like the next level, it's like this. They have that, so you see that like a crossing Y capacitance, field capacitance. I think not capacity. Okay, this one is capacitance. And then here is, yeah, okay, here, that's right. So you here, okay, here you have a middle 2, right? Middle 2 here, and on the bottom is the middle 1, and on the top will be middle 3. Okay, it's this picture. So usually when you have like even, it's not like a plan. Here you see that this one is not a plan, right? But when you have like one Y like that, you have the capacitance from this Y to the other one, to the other two, like this. This one is the they call that coupling capacitance because it's coupling from this and then the neighbor, right? Coupling. The other one is the capacitance to the ground, and the ground here is not really the sub like all the way down here. It would be the next layer because you see that middle 2 one here, but if we talk about like a middle 10, middle 11, and middle 9, then it's far away from the sub. So that like the capacitance from the middle 10 to substrate is 0. But the important is the next layer. And then one of the then when we have like, you see that this one, it will be even like even it has the gap between the Y. But when you have this one perpendicular like that, so the effect of the Y like in parallel on underneath here, it will become almost like a plate. The same thing. So which means like usually the capacitance from this Y to the lower layer or to the upper layer is called that like a ground capacitance. So you have two things. The C of the Y, CY will be C coupling plus C ground. So C ground is means like you C coupling is this one, right? But not only this, it will be like a next one too, because you have that. You have like a two like at the two sides, and the C ground is from this one to the next layer, right? So this one from this middle two to middle one and middle two to middle three. So layout extraction. So there's the tool in Celsius, which is a style. So it will extract, it will calculate those capacitance. So that to be simple, layout extraction is from the layout. It will extract to have like a system of. It will extract the parasitic, which is extract the R and C of the Y, not the cell. The cell by cell has the data in the dot lib. So the layout extraction is basically for the Y connection. So in that, it will extract two parameters. One is the capacitance and one is the resistance. Resistance is simple, right? Because you have the resistivity and then you have the Y. Then you can extract the Y resistance. For the capacitance, it has to extract. It's more difficult because it has to calculate the spacing, the width, and so on. It use like some Raphael or like a QuickCap. Those tools is very powerful to calculate this 3D model. So it takes a while to do that. Okay, then so the layers, why do they do that? They have to do that so that from there, then they can count when they have an R and C, right? Then they can start to calculate the timing of the Y. Because without R and C, how do we calculate the timing, right? So that's the layout extraction. Timing verification, those things, I think we talked about that. Okay, those things, I think maybe we don't need to. Yeah, this one, I think if you can read that, and if when you have a question, just send me email. The one is I want to share you another one. Okay, this is I think it's just to give you like the overall of like the physical design. So that in this we will talk about like it's all is the purpose again is to have a performance, power, area. Yes, I think I think it just adds like a reliability and yield. Those things is like a secondary, not secondary, but it's like later on. And then like cost, all things is go with cost. So we can read that. I just introduce now, and you can read that later because this one is I think you can read and understand. The physical design step, it will be like partitioning, floor planning. Floor planning is what I explained already. This one is just like to summarize. Power and ground routing, right? It's now to like route the power, implement the power grid so that it satisfies the power requirement for each block, for each place in the chip. Placement, so that to like to place the cells accordingly to meet the requirement for the timing. Then we do the clock network synthesis. So it will build the clock tree. The purpose is like to meet the prescribed skill and delay requirement, which is arrival time will be the same. But the skill here, I think, is along the way. The skill here is the useful skill, not the skill that we like unpredicted skill, right? Remember, there's a two kind of skill. If they ask you, yeah, is that if they ask you like, is that every clock skill is harmful or is bad? You can say that no, only the unpredicted skill is bad. Or like but there's also the kind of useful skill that we intentionally doing that, so to like to improve the timing. Then you have a global routing and detail routing. These two is yeah, I think we don't have time to explain. And whatever. Okay, so the step, it will be like from physical design, we have step to put it here. Physical verification. I think I did explain all things. It's just summarized here, right? I explained in the previous thing. And the EDA tools. So this one is a summarize of the current EDA tool using for the layout design or physical design. So for place and route tool, it's a Fusion compiler for now. For Synopsys, Cadence, and Innovus. And then you have that, okay, this one you can read and know what it is. The floor plan step, this one is good to like let you know, but this one in here, you see that first thing is we have to design the size and the shape of the block, right? So we have to do that. Then voltage area creation stuff, I think I didn't talk about that. So IO placement, so this negotiate with the other block, and then we have to put the IO at the negotiated place location. So created the sender cell row. I think explained that in the previous section, which is the cell row. The cell will be placed in the row, and then we need to create that during the floor plan step, right? And macro placement. Oh, adding routing and placement blockage. That's another one during the floor plan. I think that okay. All right, I think that this one is the step of adding the routing and placement blockage is important. Let me put it here. This one. No, this one is not. The other one will be. So, but by the way, I think just like you have adverted, right? This in all the block is just put next to each other, and the connection is by default like a by adverted. But this one is no adverted. So you have that. So you have a gap in between. So because of gap in between is reserved to like have the routing to connect between the block. And then here's I think it's like a mix between a button and channel. So this in block 1, 2, and 4 is updated along with the block 5, block 6, but the other one are not, for example. But you know what? In reality, I think basically we have this one because it's not easy at all to do this abandonment. This one need a very close and good coordination between the teams, which is nowadays is we have quite like a big teams, right? You have in the SOC, we have like tens or like 20, 30, 40 blocks in there, even 100. So to coordinate that along with everybody is not an easy task. Yeah, I think this one floor plan again is just like have it's plan of what it is done. But I want to go to this one, yeah, for example, explain a little bit for the macro placement. You see that like this one, the macro will be placed around the chip, right? And then this like this cloud here will be the logic. So you see that. So you see like because of the logic here, so it will be like together with the memory here, macro here. So they will place along the way. That's like a basic thing when we place the macro. We will like throw out a initial placement because at the beginning we don't know what it is. We just throw out a floor planning and run the placement to see. Let's say if we see that and then we see that the hierarchy 2 here, right? This macro I put it here. But this one is like stay like the logic stay here. So I know that I put the macro is wrong. I have to move that over here so that it got together. So after a while, it will go converge to like okay, whenever like the cloud will be like a place nearby the macro. So that means that this one is a good placement because like you see that there's no disruption between like in each hierarchy. The next one I want to let you know is the routing blockage and placement blockage. Yeah. The routing, for example, for the macro, let's say the macro, you need to put the first of all the placement. What is a placement blockage? Placement blockage means that when you put it down, you just set like at this one, you put the placement blockage the rectangle, right? When you put that, then the tool know that like, oh, now I cannot like place any standard cell into that. Because if I put that to here or here, it will be on top of the POF, right? It's not working. But even I put that like a next nearby that, I don't want that, because these usually in the macro we reserve the halo like that, the halo for the which means like a space around the macro, so that those things will be like used for inserting the buffer when we fix the hole, when we do the fixing thing. So we usually like have the space around that. The second thing is that when we don't have this the cell around here, then the routing has a more room to run out, right? You have this one, it go out, it will like, it's not all the routing go straight out like that or straight, because this POL, let's say not this POL, another macro, it go from here, it go up here. That means it will here and turn. So it needs room to get out the macro and go to the destination. So because of it, we need to put like a macro placement route around the macro. That's first thing. The second is we need to put like a routing blockage too, because let's say like this, let's say the RAM here, right? The RAM here, it is using up to, because the SRAM is the macro, and in macro it has also has the routing in there. And if it uses up to middle 5, then we have to block the routing on top of this up to middle 5, which is the routing here. If I go from here, right, from here I go to this one, I cannot use the routing on middle 1 2 3 4 5. I have to use up to them. I use from the middle 6 and up, because I know that this SRAM already use the middle 1 to middle 5. So that's why I think the routing blockage is important, because if you don't have it, then the tool will route that on middle 4 and go from here to here. So when you use middle 4, that means that it's like overlap with the routing inside the SRAM here. So it's not working, right? So there's two things. This blockage here is very important. You have to put the blockage so that for our purpose, but the routing blockage to prevent the tool route and the same layer as inside the macro. Also it's here, I think this one is like the placement blockage, but here's a partially blockage. So in here, let's say like, as I said, this one you need to get out, right? You have the port here, and then you need to get the signal out of the SRAM. You go out here. But let's say this one is like long, it's 100 micron. So you go from like the bottom here, you go up here, it takes like 100 micron to go out. So it cannot go out that far. So we need some buffer to go out. So that's why we need to like a block. We need to have like we don't want any cell here, but we need to allow the buffer to be inserted in this area. So that's called like a partial placement blockage, which is like it block the placement of the regular cell, but it allow the placement of the buffer or inverter. All right, I think this one is, by the way, I think this clock message, you can read that, routing push route. So I will send that later, those things. That's all like I have for the piano. So I think we might not need the, okay, now I just answer a question, so we don't need to take a break because we don't have much time. So if you have a question, just ask, and then we can, okay, first of all, if you have a question about the class, if you don't have question about class anymore, then you can ask any other question, any question. Okay, now go for the class question. For the final, so I think the final is like in person, and then Professor Then will take care of it. So this class will be my last class with you guys. So I think, yeah, that's it. So I think after that, I think we won't see anymore. But anyway, we don't see